All right, we're going to talk about page 61 through 64 in your guided workbook. This is all one example that involves Social Security outlays since the years 1975. So they're talking about a formula up here, and they're talking about if you have two coordinates, xy and xy, those are any 2 points on a graph. And you want to find the slope of the line that passes through those. Remember, the slope is the rate of change. It's the ratio of the change of the two items. It's the ratio of the rise over run. So we're going to be talking about this some more. So in this example, you have this data, and in the first example, they're saying take the first and last data points from the set. So we have 1975 made $64,656 and 2005 made $523,305. So this is how much money was actually placed into the system for Social Security during those years. Find the slope and then interpret it. So these are my x values because they are the first values in the ordered pair, and these are my y values because they're the second values in the ordered pair. For no particular reason, I'm going to call this 1 and this 2, just because that's the first point and the second point. So according to the formula at the top of the page, it says take y2 minus y1 and divide it by x2 minus x1. So we have y2 minus y1 so that's the 523,305 and the 64,658, and 2005 is x2 and 1975 is x1. So if I do the mathematics, I end up with 15,288, and I'm going to leave it over 1 because we want to represent our slope as a ratio of something, so I need something to compare it to. So what does that mean? That means that for every 1 year since 1975, the Social Security outlays have increased by $15,288. It can be said a number of different ways, like the Social Security outlays have increased by $15,288 every year since 1975. Either way, it's the same idea. All right, so on the next page, they ask you to take all that information and put it on a graph. And so you notice that you have these points that are plotted for you. So in 1975, it was about 64,000. In 1980, and then in 2005, it was 523,000. So they ask you to draw a line between those 2 points. So I'm going to connect this point to the end point, and when I draw a line, this is what it looks like. So notice some of the points aren't on the line. That's because they might have been a little bit lower. So what we're dealing with is a situation where it's not a completely, the ratio is not the same every single year, so it's not completely, it is linear, but it doesn't have the same rate of change. So it says compute the line y equals mx plus b, by plugging in xy and xy point and the slope m. So we got that slope on the other side. That was the 15,288. And we're going to use the point 1975 and 64,658. It does not matter which point I used on the graph. I could have used the 2005 and I would have gotten an answer similar to this. So I'm going to take the y value and put it in for y. I'm going to take the m, the slope that I got from the other page, and put it in here. X is the 1975, and I'm going to find b. B is what we call my y-intercept. So B equals the y-intercept. So that means that's the point where it's supposed to cross the y-axis. And I end up with B is negative 3,012,000, sorry, I've got to put my commas in there so I can see it, but negative 30,129,142. So then when I substitute that back into the problem, this would be my linear equation for this problem. Okay, so when I drew this line up here, if I looked at this, where does it look like it's actually crossing this y-axis? So if I asked you to estimate, it's below 0, a little bit below 0. So I said, what if I said that it crossed the vertical axis at about -5,000? But according to what this says, the y-intercept is supposed to be -30,129,000. So why doesn't this graph reflect -30,129,000? So the reason for that is because the graph at the top starts at 1970. It doesn't start at 0. So when you're talking about years, it really doesn't make sense to say a 0 year. I mean, that would be, you know, way back before 1970, before 1960. Social Security didn't even start until the 1930s. So it doesn't make any sense to try and go back to the year 0. So we have to think of something realistic, and we change our data a little bit. So on example 5, you'll see what we did here is we took the table that we had at the beginning, and instead of using 1975, we said years since 1975. So we said 0. And then 1980 would be 5 years from 1975. 1985 is 10 years from 1975. So basically what I'm doing here is I'm subtracting 1975 from each of these values. And that's what I get with these numbers. So now I do the same thing. I calculate my slope, but I'm using 0, 64,000, and 30, 523,000. So I end up with 15,288.23, which is pretty much what I had last time. But this is my equation this time. So my y value that I used this time was 64,658. My x value was 0. And if I go into this equation and I put the 64,658 and I put 15,288 and I put 0 for x plus b, I end up with b just equaling 64,658. So this is my y-intercept. Okay, so I'm using that value for b. So this is my equation for my new line. So that's saying that the 64,000 means that at year 0, it would be 64,000. When year 0 this time is 1975, because that's when we're starting to collect our data. Okay, so now what I did is I took the same set of data, but I put it into my Excel spreadsheet. And what I did is I created a trend line in my Excel spreadsheet. And so I'm going to show you really quickly how to create a trend line. Sorry, I've got to open that file up I have. Okay. So here I have the data that we just typed in, the 0 through 30 and the 64,000 through 523. And I created a scatter plot, and so you can see it looks pretty much like what we have in the book. So if I click on any one of the points, you'll notice that there's like a little bit of a dot that appears next to the point. And if I right click on that, it says add a trend line. So my choices here are exponential, linear, logarithmic, polynomial. We're dealing with linears right now, so we're going to choose linear. And then we're going to scroll down a little bit, and right here it says display the equation and display the r squared value. And you'll notice that what we have here is the exact same thing that you have in your book. And this is what we call a trend line. Okay? So now, back to our book, if we look at that, it says, use your line, sorry, let me get that out of the way. use your line, X years since 1975, and the line of best fit to predict the Social Security outlay. So the line of best fit is that equation that's on the chart. So in 2012, that is 37 years since 1975. So if I substitute 37 in for X for this equation, I end up with 600,629. And now I'm going to take the equation that I had on the previous page that I got using my two coordinates, and I'm going to substitute 37 in, and I get 630,314. So in actuality, in 2012, it was $808.04 billion was the actual amount. So which one's closer? Our line that we calculated was closer. So what we have to understand is that the changes seem to be growing a little bit differently than just linear. What we're going to find, what we're going to find is that as the years were increasing, the rate was changing dramatically. So here we had 630,000. Oh, I'm sorry, it was 630 million. If we look at the chart, 630 million versus 808 million. So we are looking at, that's why the change is a little bit closer. So I hope this helps.